Yes, this is the day of first flight of the Xb70. To tell you about today's events, Mr. Tapscott.
This is Mark Tapscott reporting to you for the United States Air Force. We are at Palmdale Airfield in California, some 80 miles northeast of Los Angeles. Tense expectation prevails here this morning, for this is the day the Xb70 gets its first taste of air. As more than one airman has remarked, this plane looks like it's in flight, just standing still. The maiden flight of any new aerospace vehicle is a matter of national significance. We are here today to watch the Xb70 taxi out this ramp and take off from the runway out there. And to understand a little of why this aircraft has been called a national aeronautical achievement. The countdown for today's flight is already underway. The plane is fueled and ready, and the two men who will pilot her are making final preparations for the flight. We take you now to our reporter inside the pilot's ready room.
These are the men chosen to perform the first flight test of the Xb70. Chief Test Pilot Al White of North American Aviation and Colonel Joe Cotton of the United States Air Force. Both men have put in long hours preparing for this day. Al White has been a part of the Xb70 program almost since its inception. An engineer in his own right, he literally grew up with the bird he is to fly today. Al, I wonder if you'd tell us some of the highlights of the flight today, like when you'll be hitting Mach 3.
Well, let me set the record straight. By today's standards of speed and altitude, we're not going to do anything spectacular on this flight. We bite off what we can chew. This is testing, not stunting. Just because we have a Mach 3 machine here, a lot of people expect us to go full bore right away. This is not the case.
Well, I stand corrected. What are the facts?
Well, we'll definitely not attempt a high Mach number on this initial mission. We do plan, however, to go to an altitude of 35,000 feet and a speed of something over Mach 1.
That's around 700 miles per hour at 35,000 feet. Is that right?
That's right. And we don't plan to go too far either. We'll be operating in the test area, just north of Edwards. Let me show you on the map. This is Palmdale, and to the north, at Rogers Dry Lake, is Edwards. We'll be operating in this flight test area, just north of Edwards. We'll be terminating the flight with a landing here, at Edwards. Plan is to be in the air just under 2 hours. But I'd say it really, how long we fly and how much we do will depend on the way the systems perform. If they're not up to snuff, we'll probably land early.
You understand we'll be feeling out the machine. Flying a new aircraft like the B-70, we'll have a lot of new experiences to absorb and record. We'll have a recorder aboard, taping every word we say, and we'll be answering a lot of questions on handling characteristics. In fact, about 15 cards full of questions. In addition, there'll be sensing devices all through the aircraft, picking up the stresses, strains, and all sorts of flight test data.
Obviously, you don't just jump in and fly a plane like the Xb70. Colonel Cotton, what kind of experience do you have to qualify for this job?
Well, I guess you just have to have been scared several times before.
All kidding aside, Joe was one of the original Air Force B-58 test pilots and has extensive experience in testing heavy aircraft. I had the good fortune to go through the B-52 Combat Crew Training School a couple of years ago. More recently, we've both been flying the B-52, the B-47, and the B-58 in preparation for this flight test program.
I think that simulator time is very important also. You might say that we've faced and solved many of the problems on the ground before we ever get in the air.
I understand you can fly the Xb70 in shirt sleeves.
Yes, that's why we can wear these light flying suits. We'll keep the cabin temperature around 75 degrees, and the cabin pressure will be similar to what you would experience in a jet transport today.
Later on, when we go to a high supersonic speed, the aircraft will heat up on the outside, but we'll still be able to keep comfortable inside. At Mach 3, for example, the skin temperatures on the outside of the airplane will build up to from 450 to 650 degrees Fahrenheit. This is all due to air friction. That's just a little hotter, you might say, than the inside of the average baking oven.
Well, Joe, we'd better get back to work on our flight planning here. Will you excuse us, please?
One last quick question. Do you have any butterflies about this flight?
Well, I'd rather not speak for Al, but for myself, you might say I'm a little nervous. Maybe something like when you're getting ready to give a speech. I guess that's okay because even some of the experts say that's the way it should be.
They've designed a good airplane here. I'd say the chances of anything major going wrong are about 1 in 10,000. Remember, this aircraft, in a sense, has flown before. Thousands of hours in wind tunnels and simulators. More time than any other aircraft flown to date.
Thank you, gentlemen, and good luck. While the stage is being set to fly the Xb70, other men are still at work on the overall program as it exists today. We switch you now to the North American plant in Los Angeles.
We are located in one of the conference rooms at North American's Los Angeles division. The meeting underway is to discuss the Xb70 program schedule. Colonel?
Yes.
Colonel, we understand you are now operating under a two-plane experimental program. Would you care to discuss the status of the two aircraft?
Certainly. As you know, plane number 1 is now ready to go at Palmdale. Plane number 2 is nearing completion.
Are there any differences between the two planes?
Basically, the aircraft are about the same. However, we have made some changes in the wing of the number 2 plane, which will act to increase the natural stability of the vehicle. In addition, the instrumentation in the number 2 plane is more sophisticated, so as to assist in gathering data to be used in the National Supersonic Transport Program.
Did you have any trouble building the plane?
Definitely. This aircraft represents significant advancements in the state-of-the-art development almost across the board. Power plants, metals, manufacturing techniques, the works. As you are probably aware, the manufacturing problems alone have caused delays in arriving at this first flight date. The lessons learned on this first aircraft, however, have proven invaluable in producing the second plane. Now, for a more detailed answer on the nature of our problems, I'll let one of our project engineers take over. Tom?
Thank you, Colonel. I believe the best way to illustrate this point would be to show you a short film made up of clips taken from our official reports. But before we look at it, let me say that the heart of the problem centers around Mach 3 speed, which means heat. This disqualified aluminum, and steel became the material used.
Here are men working with stainless steel, as men have never worked with it before, because we have never built an airplane out of stainless steel honeycomb before. There was the problem of bonding steel sheets together by brazing methods, learning how to join sections by welding instead of riveting, ending up with a lighter, smoother, flyable steel shell able to slip through both the sonic barrier and the thermal barrier. Here is testing underway with an escape capsule for the crew of the Xb70. Water tests to prove it will float and sustain life. Drop tests on concrete to prove it will absorb shock. Sled run tests to prove the reliability of ejection mechanisms. And the rows of heads bent over drafting tables, the never-ending blueprints. Red-hot steel being forged for a landing gear that will handle 250 tons of weight. 13,000 hours of wind tunnel testing, checking theories, correcting design. Building one of the most powerful jet engines in the free world today. And the air ducts to feed the engines. Designing an inlet port that can vary the input and speed of rarefied air. Thermal testing. Lamps producing over 600 degrees of heat, burning down on a model of the fuselage cabin. Instruments to measure inside temperatures. Humans must live and work here. No other plane has ever had to sustain such heat for so long a time. Manufacturing tires that will not bubble and crack under 350-degree heat. And finally, solving the complex problems of assembly. Welding large sections together under conditions where the smudge of a fingerprint spoils a weld. Giant cranes swinging wing sections into place. Prefabricated stabilizers bolted down. Sliding engines into waiting ports. Wiring and cabling from cockpit to tail. Wheels and struts assembled and then checked in operation. Parts and components and sub-assemblies from 100 contractors moving to Palmdale to create the world's first stainless steel airplane. And then comes the day we've all waited for. The day of rollout.
It is approximately 184 feet long with the special instrumentation on the nose. It runs approximately 196 feet. The wingspan is about 105 feet, and to the top of the vertical fins, the height is approximately 31 feet. The weight, much greater than that of a B-52 in our latest configuration.
These film clips, I expect, gave you some impression of the difficulties one faces when speed is the object and heat is the obstacle. For this airplane is built to withstand temperatures that planes built with conventional metals and techniques could not tolerate. Colonel, I think that about covers the subject.
Thank you, Tom. Now, if you have any further questions on the use of stainless steel honeycomb in the Xb70 or on the aerodynamics of the aircraft, I suggest that you take a look at our full-scale mock-up.
Colonel, you have been most helpful. Thank you.
Not at all.
The mock-up referred to is close by. But before taking you there, we'll switch back to Mark Tapscott at Palmdale.
I've just learned that Al White and Colonel Cotton are ready to make their pre-flight inspection. The test pilot is a curious blend of pilot and aeronautical engineer. He loves flying, but he goes about his business like a strict professional. This is the impression we get today, as White and Cotton meticulously check their aircraft. This inspection will take some time, so we switch you now back to Inglewood and the mock-up hangar.
This is the entrance to the Xb70 mock-up area. Until recently, passage beyond this door was restricted to those holding a confidential clearance. Today, we can enter and see what many military and civilian officials have come to view over the past 4 years. This, of course, is not an actual aircraft. It is a creature of plywood, sheet metal, and plastic, a make-believe aircraft. But in its own way, this life-size model that will never fly is as much the spirit of Mach 3 flight as is the Xb70 at Palmdale. It was here in the early days that countless people came to look and to imagine, to plan and to work. It was here, with the design and manufacturing story displayed for all to see, that the questions were asked, concepts explained. Today, we can ask some of the questions, and a representative of the Air Force is here to answer. Colonel, we're all ears.
You haven't asked me a question. I don't feel at home unless a question's tossed at me.
Okay, so what is the thermal barrier?
In a sense, the term thermal barrier is a convenient phrase. Thermal, of course, simply means heat. But there is no wall or barrier one suddenly runs up against. You see, the faster any aircraft moves through the air, the more heat is built up by air friction and absorbed by the plane. If you'll recall, on the astronauts' re-entry into the Earth's atmosphere, friction with air caused the capsule to become extremely hot. We have the same principle on the Xb70, except the friction is not as much, and the temperatures experienced are not as high.
By thermal barrier, then, we really mean the point where the strength of metal begins to fail when used in conventional aircraft construction techniques. Now, here was the problem. We wanted this plane to travel at Mach 3. At Mach 3, temperatures, as you probably heard, build up to well over 600 degrees. Now, step number one was to find a suitable metal that would withstand this heat. Aluminum, the standard metal for aircraft construction, was definitely not strong enough. We finally settled on steel. But steel, as you know, is heavy, and this brought us another problem. To solve this, our engineers took a lesson from the bee and designed a honeycomb structure like this. The final result was this: honeycomb steel paneling, light yet strong. In fact, honeycomb steel paneling is many times lighter than a solid hunk of steel the same size, yet many times stronger than a solid piece of equal weight. But stainless steel is not nearly as easy to work with as aluminum. So new methods of welding and brazing had to be devised.
Colonel, our audience has already had a look at how you braze and weld.
Fine, then I won't go into that. Now, even though stainless steel can stand the kind of temperatures we're talking about, we still had to find ways to stop the heat from building up inside the aircraft. The air in the honeycombing serves as good insulation. The heat that penetrates this insulation is absorbed by fuel stored in large tanks in the fuselage and wing. This fuel soaks up heat like a sponge soaks up water. In addition, the working parts of the aircraft, the crew compartment, the navigation area, the whole front part of the nose section there is cooled by refrigeration.
That's quite a battle you people wage against heat.
That's right. Heat is the problem because of speed. You remember, this plane will cruise 2,000 miles an hour all the time, all the way to a target and back.
And I suppose it goes without saying that maintaining this speed comes from the power of the engines.
Yes, but it's not quite that simple. Speed comes from the engines, of course, but maintaining it at high altitudes for a long distance with a heavy payload aboard is made possible by several new aerodynamic principles, some of which I'll explain later. For now, let's move to the aft end. While we're here, these scale models offer an interesting comparison between the Xb70 and the current B-52. As you can see from the silhouette, the Xb70 is slightly longer but not nearly as wide as the B-52. Now, let's walk down here. Power for this airplane is generated by 6 General Electric J93 engines. Just one of these engines has the horsepower equivalent of 50 diesel locomotives, or enough power to light a city of 60,000 people. This power plant will push the Xb70 along faster than a bullet from a high-powered rifle. Also important from a maintenance standpoint, all of these engines are interchangeable, and any one of them can be completely installed in 30 minutes.
I'm impressed.
Let me impress you more. Come down here with me. Ever since the days of the Wright brothers, aircraft have depended upon the lift produced by air flowing over the wings. So does the Xb70. But it also gets a bonus lift from a new concept called compression lift. This is one of the aerodynamic principles I mentioned earlier. I could use a lot of technical jargon to explain it, but to simplify, think of it in terms of a speedboat. During supersonic flight, the lower fuselage produces a shock wave in the air comparable to the bow wave of a fast-moving boat. This shock wave extends back under the wings, creating positive pressure, which gives extra lift to the aircraft.
Colonel, this compression lift, has it ever been used before?
Not in this way. This is the first aircraft specifically designed to use this principle. You'll discover there are many firsts on this aircraft. Another design feature that's unique is the folding wingtips. When the Xb70 goes supersonic, the wingtips are made to fold down to give greater stability during high-speed flight. I'll show you what I mean. At high speeds, we require increased vertical surfaces to provide satisfactory directional stability. Now, the folding wing principle allowed us to design smaller vertical stabilizers than would have been otherwise possible. This results in less drag on the plane, more efficiency, and more range. we have another set of control surfaces up forward. This is the canard, or forward-mounted horizontal stabilizer. It is not a first for the Xb70, however. Very early aircraft of Kitty Hawk design used the canard. And now, having practically disappeared for 50 years or so, it's back with us. The canard balances the aircraft. It is the fine adjustment that keeps the plane in a good attitude for flight. Trimming it, in other words, as the center of lift changes as speed is increased or decreased. Now, if there are no further questions, that about ends our $1.50 tour.
Appreciate your time, Colonel. Thank you very much. The achievements of the past and ideas for the future are contained in this room. To get back to the reality of the present, we switch you now to Palmdale and the first flight of the Xb70.
All 6 engines are running now, and completely dominating the scene is a feeling of suppressed power waiting to be unleashed. From this point on, until after the 70 leaves the ground, we'll sign off and let you listen to the voice tape between the pilots and ground control.
Palmdale Tower, 001, how do you read?
Good morning, 001, Palmdale Tower, here's you loud and clear.
Roger, we're ready to taxi.
Roger, cleared to runway 7 via taxiway Bravo, wind 090 at 8. Maximum velocity last 2 hours has been 10 knots. Cleared for takeoff 190.
Roger, thank you. Wind's on the east, huh?
Affirmative.
The brakes are off now, and we're rolling in.
Roger, out, good luck. All stations of network, the B70 is now taxiing out. Come on. Edwards, data control, Mobilcom. Go ahead, Frank. We are now taxiing. Roger, thank you.
Ground interphone. Switch is off and it's a little more quiet now. Turn it back on. Turn it on again, Frank.
Are you talking to me, Frank, 001 in?
Negative, Al. This data control, Al. Do you read me all right?
Loud and clear, Max.
Right. Mr. Spivak says you're looking great, Al.
Good, thank you.
Mobilcom, Chase 2 and 3, all right, boys.
Roger, Chase 2 and 3, this is Mobilcom. Chase 2 and 3, is that affirmative or airborne? This is Edwards data control. Now, this is data control. We have you on a TV monitor. You look great.
Thank you.
Attention all stations, 001, now taxiing through the gate. Side 1, Roger.
Palmdale Tower, Chase 2 and 3 approaching from the north.
Chase 2 and 3 approaching from the north, Roger. The B70 is coming out the gate.
Any local traffic?
Local traffic, Chase 1 and 2. Attention all stations, 001, now making turn to taxi west. Edwards data control, this is Edwards Tower. Chase 1662 is on the runway for roll now. Roger, thank you, Tower. All stations of this network, this is Edwards data control. The Xb70 is about to line up at the end of runway 7 in Palmdale.
Everything is looking very good up there, and we're all set to go.
Roger, Al, you're looking good yourself.
You ready to get going here?
Let's go.
Data on at 7825. Coming up on tower.
The torque should decrease. Our ammonia light is out. Rear shut off, push in.
10 seconds. 5, 4, 3, 2. Brake release now. Rolling me.
flight. From all reports that have come in so far, the flight is going well.
Okay, I'm going to finish this turn. I'll be headed down here at about 60 degrees, and we'll pull the gear up then.
Some 32,300.
If all systems and controls continue to operate okay, Al White will soon retract the landing gear and take the aircraft to altitude for a try at Mach 1, his goal for the day. When the Xb70 is pushed to Mach 3 on some future flight, it'll be moving faster than the Earth rotates. From this spot in California, it could travel to New York in an hour and a half, to London in 2 3/4 hours. Just a moment, Al White is back on the air.
You ready, Chase?
Yes, sir. Yes, sir.
3, 2, 1, gear up now.
Okay.
Okay, they are static, is that right? They're not moving?
That's correct.
Okay, I want a confirmation from the ground to go ahead and put the gear handle back down.
Roger, let's go ahead and put the gear handle back down. And when I put it down, the right light went out. Right green on, left green on, data's still on. Main gear doors are still open.
The difficulty in raising the landing gear, though in itself a relatively minor malfunction, comes as a sharp disappointment to a great many people. It means that no attempt will be made to break the sound barrier on this historic first flight. However, the flight will continue with the wheels down for data gathering purposes. Now, with the data gathering mission completed, the Xb70 comes in for a landing at Edwards Air Force Base. That puff of smoke on touchdown indicates some further trouble with the landing gear. From here, it looks like one of the brakes may have locked. However, the main objective of the day has been achieved. The Xb70 flies.
Yes, the Xb70 flies. The malfunction proved to be an easily repairable defective brake. And within a few days, the Xb70 was back on the runway at Edwards Air Force Base, taking off on its second flight. Two more flights were made within 29 days, reaching preliminary goals of 45,000 feet and 1,000 miles per hour. On the fourth flight, the wingtips were folded 25 degrees for improved directional stability at transonic speeds. On future flights, at higher supersonic speeds, the wingtips will be folded downward 65 degrees. We can be proud that this nation has pioneered a craft that can ride the Earth's atmosphere at a constant speed of Mach 3, with potentials for even faster flight. The skills and knowledge gained have already made a significant contribution to aerodynamic vehicles of the future.